I hope everybody had a nice lunch and is nicely full and tired now, and I can provide a little bit of background noise to your little nap here. Anyhow, I'm the managing director for the Energy Campus of Nuremberg. The Energy Campus is an energy research institute. I used to be very active in the OPV community. I used to be the managing director for Nanotechnology Technologies GmbH, so the German branch of Nanotechnologia. And I was co-organizer of the ISOs 2, and I think also ISOs 3, but I can't quite remember. It's been a little longer. I'm almost part of the inventory at ISOs. We've come a long way, but let me start and say a little bit about where I'm coming from now, what I'm doing now. I come from Bavaria, and in particular, northern part of Bavaria. We have a lot of companies, 14,500 companies, 111,000 employees, and 27 billion in turnover in the energy sector. That is, of course, everything in the energy sector. And because there's a large need for a reorientation in this Energiewende that we have going on, we established a new research center over there. And this research center is based on the assumption that you have to look at the whole system if you're going to introduce a large amount of renewable fluctuating energy sources into it. We're doing everything you expect there. We're working on from the generation through transport and storage, through utilization. We're doing material science, electrical engineering, all the engineering and natural science disciplines, and we're also including the human factor in it. We're unlike Soliance, we have our own building at least. We're also a cooperation of 6 research institutions. We have a building with 5,800 square meters. We have laboratories, technical facilities in all the areas that we work in. I'm going to skip this 6 institutions, and our connection there at the Energy Campus is that we also have a competence center that's called Solar Factory of the Future, and it is working on printed photovoltaics, not organic photovoltaics necessarily, everything, every technology that you can print. With this, I'm going to end the introduction to what I'm actually doing most of the day and get back to something that I do a little bit as a hobby, and that is standardization for photovoltaics, for nano-enabled photovoltaics, we've called it. New types of photovoltaics. Why are we doing this, and where did this come from? It actually all started with ISOs, but there are good reasons for doing what we do. So there are standards around, and we already talked about those in 2009 or 2007 even, and everybody knows IEC 61646. It comes up in every conversation about standards that might be relevant. But these types of standards and the equivalent ones for silicon or for thin film, for other technologies, they're meant to qualify products, final products. They don't really help you anything during the development process for a new technology. And organic photovoltaics is a new technology, and it's not at the stage where we have a serious product out there where it would even make sense to test according to this. Rather, this community is in a stage where you are trying to improve the technology, you're trying to achieve a state where results can be compared, where you sort of develop a yardstick for how to actually gauge stability or to develop processes by which you do things. Right now, there's still a lot of searching around for what is the best way in various places. And through some simple standards, you can actually aid the community in taking existing experience, wrapping it up in a document, and then making it referenceable. We believe you can come around much quicker into realizing the full potential of a technology. We think that through standardized processes, development times can be shortened, and especially because common mistakes can be avoided if you have documents out there. But these types of standards that I'm referring to, we call technology level standards, and these types we don't have yet. And here I'm going a little bit into the history. So this is from ISOs 2. This was from a similar session as I'm chairing this afternoon, except back then I chaired it with Darren Laird. And this was a result of this session, and it's actually it's a really good picture. There are different. We talked about what has to be done, and there are really different levels of testing that come into play. There's this sort of developmental testing, we called it. For example, for extrinsic and intrinsic stability. I'll talk about that in the next slide. And these are very mechanism specific. So you might just expose something to oxygen, or you might expose it to water, but there really is no reason to standardize something like that, because you actually don't really know what you're going to find or what you're really looking for. And then above that is when you have some understanding and you get to you've actually narrowed down to a system that you reproduce more often, you come to a level that is where you try and test the system stability. You try to understand something that you now can produce many times, you can reproduce it, and you want to know how stable is it. And at that level, I would call it the technology-specific testing, because the types of tests you want to use there should be different for a standard amorphous silicon compared to an OPV or similar types of technologies. And then later on, you come to this level where you actually come to a product level, and here you do product testing. And again, that would be very specific. I carry around a bag with an OPV panel on it. If you want to test that, you'd probably do something very different from what you would do if you want to actually put a panel up on a roof somewhere. Or it might also be very different from what you might do if you want to put it inside a glass pane. So these would be very application specific, and in the end, they will probably come from the people that sell the final product rather than from a community here. So actually, I firmly believe that these types of standards that we need for a community like this, and we already found that out back then, should be in this technology-specific area. Why I do this is, this is a slide also from, this is actually from ISO 1 from 2008. I think it demonstrates pretty well. There are many ways to do things like accelerated aging, and there are all sorts of tests that you can do, and some are more sensible and some are less sensible if you actually want to develop compare stability. And I don't think I need to comment a whole lot more on that. It's about, so this standardization that we've embarked on is really about finding the tests that make sense. And that in a very complex environment. This is also an old slide. So here we're talking about, we have these stress factors that come in when you talk about stability, and we have somewhere a cell, then we have packaging around it, and we have sort of intrinsic degradation that happens here in these active layers, but we also have extrinsic degradation. Yellowing of a packaging film is an extrinsic degradation, but it'll still decrease the performance of your cell. And in the end, the lifetime is really a system property, and actually, I apologize, the slide is from 2009. Today, I wouldn't really use the term lifetime anymore, because it's really misleading. What we can talk about is stability under certain conditions. I don't know anybody that can make a real prediction about lifetime. So I will always use stability. And anyhow, back then, it was pretty clear to us that we needed some sort of guidelines as to how to do testing, and that's why in 2009 we made a first draft, these recommended practices, and published that. And in 2010, actually under the lead of Frederick Krebs, and then Matt Rees and Søren Gevorgian actually did most of the work on this, I believe. We came up with this paper that is now often referred to as the ISO standards. And actually, this was a list that was a little more simple in my opinion. Here we added very many things into it, and this is a very comprehensive work, and it's a very good work, and it has been effective. But it has one problem. It's nothing else but a paper that is published in Solmat. So if you want to have a real standard, you have to do something different. You can't just publish a paper. So where do real standards come from? And I think it happened sometime in 2010. I was approached by the DKE, that's the German Commission for Electrotechnicals, and and the IEC, and they asked me to present some of the work that we actually had done here in ISOS and the results that we produced. And we have now, with those results, embarked on really making a real standard. When you do that, you need some standardization committees. And there are various committees that are out there. There are national ones, then there's regional ones, and then there's international ones. And they have different areas that they're working in. And most relevant for what we do is this branch here, and it's really the IEC. And the DKE is the German branch or the German arm of the IEC, where we have the local German subcommittees. And through the IEC, I'm now a member of this subcommittee that's called TC113. It's Nanotechnology Standardization for Electrical and Electronic Products and Systems. So it's not the immediate connection to photovoltaics, because there is also a subcommittee that works only on photovoltaics, solar photovoltaic energy systems. And then there's another, the Technical Committee 119, and that is working on printed electronics. And in the past years, we've actually done a lot of communications between these technical committees to clarify who's working on what. And when you talk to TC82, they are mostly busy working on product-oriented standards. And back in 2009, I had actually approached them and asked, said, hey, we did this work in ISOS, is there something we can do with them? And I never heard back from them. And I know why, because they were busy doing standardization for PV panels, so we're going to get strapped to a roof. They're busy on something completely different. And this TC113 that I'm a member of is actually working at a different part of this value creation chain, and they really make these technology-oriented standards. That's why this work that we've done in ISOS was actually perfect for this committee. And then this TC19 is relatively recent, and they're more on process-oriented standards. So product, technology, process. That's what distinguishes these subcommittees from each other. What happens in the standardization process is something that takes a lot of time, a lot of patience, and I'm usually a pretty quiet person, but this has really got my pulse racing many times. But anyhow, there are all these stages here, and right now, so we've taken this work and we turned it into something that's called a preliminary work item. Then it was entered into this proposal stage as a work item proposal. It has now gone on into this stage, the working draft stage, preparatory stage. So we're on stage 2 of 6, and I've been doing this for roughly 4 years now. So if you extrapolate, you can imagine when we're going to reach this, it's going to take us a while. And in between, there's a lot of voting, there's circulating, there are international phone conferences where you're on video calls at crazy times of the day or night, and you have sometimes very strange discussions. But anyhow, we are making progress, and we're going forward. But what you should also know is that the IEC has more than one product. There's not just one type of standard. There's various different levels. The highest level is probably this international standard that is very normative. And then there's, these technical reports on the other end of the scale, which are more informative. And right now, there's a lot of discussion about what we do here, and whether and where to go and how to do this. Right now, we are actually working on a technical report. We're not working on a real standard. But this technical report will nonetheless be published under the IEC label and therefore be referenceable. And that's important to us. So let me now come to the actual drafts, what we are working on, and tell you a few things about this. There are actually 2 working drafts I'm going to be telling you about. So these working drafts come out of the nanotechnology area, and here we're talking about reliability assessment. It's called part 2.1. That's an interesting number. because there is no part 1 and there's no part 2.0. And yet it is called part 2.1 because it gives you room to put something on either end. So this is also something I had to learn. Then here, it's not about OPV. It's about nano-enabled photovoltaic devices. We wanted to be broader than just OPV. We wanted to capture all technologies that use nanomaterials. And we're doing a stability test. The model device that we're working on is relatively simple. It has 2 electrodes. It has an active light conversion area. It can or cannot be packaged. It depends, whatever you want to do. And you have to be able to do an IV characterization. That's about all the requirements that we have for you there. More important, though, than this picture of this 2-terminal device is really this general philosophy that we're following here. So right now we're targeting the technical report status, and with the goal to provide guidelines that can be followed for testing, similar to what we were doing with the ISOs documents. We want to perform technology testing, and this is very important. We're not making any claims about a product. We're making no claims about lifetime. That was the second time I used that, but only to say that we're not making a claim about that. What we're trying to do is just define stresses and procedures to establish comparability. And here's, for me, this is important. We somehow want to make something like the standard meter, the yardstick for stability that you can use for whatever technology you have, so you can compare 2 technologies and say this one is more stable than this one under certain conditions. Then what we also think is very important, we want procedures that can be used by certified testing laboratories. So possibly you have a technology you have developed and you think it's really good, and now you want somebody else to verify that, and you want it, of course, to be an accredited laboratory. They can't just test to any procedure that you want to, but they have to they have to have standard procedures. And by publishing this document, we would actually jump over that step and make that possible. Well, we're trying to recommend a sequence of tests without making it binding. So you don't have to do all the tests that we recommend. We're just saying, if you want to test for stability and you actually want to make a claim about outdoor lifetime, you cannot just do, what did I see this morning, illumination by 1 full sun for X hours. That says, it also said lifetime on there. It says nothing about lifetime. Because when you go outdoors, when you go actually into the field where you operate this, there are many other factors that will influence the stability. And I'm sure that the degradation will be very different from what you see under that 1 sun illumination. Although I agree, it's an important test. You should be doing that. You just shouldn't be saying it lasts 20 years afterwards, unless you're very specific. And we want to establish the actual reporting requirements so that comparability can be achieved. So what are we doing? To come back to this picture, we've defined the scope that puts us exactly in there. The approach that we've taken is fairly easy. We're defining the stress factors. We recommend values. We're defining general procedures. Throwing them together, you get standard tests. You have a number of standard tests. You have a recommended test sequence. You define the reporting requirements, and at the end you have a testing report. So relatively simple. Here's the overview of these tests. We have so standard testing for stability, like a full stability program, should, in our opinion, include probably all these tests. Some of them are easier, some of them are more difficult. So I would always start out with easier tests and then move up to the more difficult ones as I get more confident. And that's what we're trying to suggest with this arrow. Do the easy tests first. When you feel confident that you have achieved a certain stability, then you can move on to more complex tests. Stability testing is a long, arduous process. You need to be patient, and it's not all that much fun always. And then we defined these tests. So all these tests were on the slide before. We have put some parameters behind, and then we've gone and defined the actual way that you're going to go about carry out these tests. This is not finalized. Why is that on there? Because it has not been in the working draft. It has not been approved by the full international committee. That's why it's not finalized. Just to remind you, this is from the ISOs 2. And if you see a certain similarity, that is intended. So, so much for the stability testing. I also would like to tell you about some other work that we have been doing in the past 1.5 years. We've gone on and looked at the measurement of the performance of tandem devices, because one thing that we saw out there was that there's a lot of European projects, at least, that are moving towards tandem devices, and there's very little comparability between the measurements that people do, and everybody goes out and sort of makes up their own equipment to measure tandem devices and develops their own approach. So that's something we wanted to address and look at what ways are there of actually doing this. And what we're looking for was a robust measurement method that is simple as possible. It should be fast. It should be generally usable. So you shouldn't need a lot of characterization beforehand of the devices, of the individual subcells, for example. And it should use as little specialized and expensive equipment as possible. That actually is a lot to ask for. And what is the problem here? The problem when you have a tandem cell is, of course, that these are usually connected in series, and that the light has to pass through one cell in order to get to the other cell. So the standard approaches that you use when you have a mismatch factor will not work, because you cannot do an easy external quantum efficiency. What you need to do is you need to bias one cell, and then you can measure the EQE of the other cell, and then you switch it around. You also have to apply voltage biasing. It gets fairly complicated fairly quick, and we searched the literature, and essentially to us it all seemed to fall into these three classes. There was a method developed by EnCN. This method was relatively complicated from our point of view. It involved measuring the absorption spectra and doing simulations of the devices, and you do afterwards you have a very detailed analysis of your samples, but it's also very difficult. I mean, it was unreasonable to expect that every lab that makes tandem cells can actually do this. Then we found an extremely elegant method that is practiced at NREL, but it uses a really highly specialized piece of equipment. This one sun multi-spectrum solar simulator. I've actually forgotten what it's called, but it was great, as it drives the sample with 9 different sources, essentially, and you can mix all these lights together, and you can measure triple junctions, quadruple junctions. I think they went up to a hexa junction. It's very complex. It's very elegant. It works well, but we didn't feel that you could expect a standard laboratory to actually have this piece of equipment. And then we found a third method that was published by ISE, which it's sort of the poor man's version of this, and it only works for tandem cells. But there, it's relatively easy. You don't need reference samples. It seemed to us like a good compromise. So it was described in 2010, and not a very widely circulated journal, but it only has 2 steps. You increase the bias light until the EQE levels stabilize, and then you can estimate the electrical bias, and then you do some calculation, and you know what light you need to use in order to drive your cell and measure your efficiency. This is the light bias part. So here it's shown for the top and the bottom cell, and what you're seeing is they're increasing this bias light and measuring the EQE of the other cell, and after a while this EQE shape doesn't change anymore. So now you have the shape of your EQE. You can do the same thing for the other cell. Then you put bias voltages on, and you start up here, and you start look when does this EQE change again as you apply bias voltage. By that you can estimate the absorption edge. There's also other ways to estimate it. But now you have the EQE shapes. Now you get out your calculus book and do a little bit of math. It's it's challenging, at least for me. But it's doable. And that will tell you what currents you need to set your light sources at, and now you can actually measure your efficiency. We thought this was simple enough that everybody can do it. It doesn't have very high requirements on the actual equipment that you can use. And if we now just defined the steps that you have to take and the procedure well enough so that it passes the quality needs of certified testing laboratories, then this would be something good. With this, I'm going to come to an end with a few conclusions. First of all, as I'm learning, standardization takes time. I'm not quite sure how much time it takes, but it is making progress, but it's a process of consensus, which can be very exhausting. It can aid technology development. I think that's very important, and I think we can actually use this process in many more places than it's used at right now. We have some documents that are in progress. There are opportunities to start other documents. We're open for that. The stability document is progressing, and this tandem efficiency measurement document is now in its initial stages. Thank you for listening.
Jens, for the very interesting presentation, also staying exactly in time. We have time for a couple of questions. If you have them, I see one at the back.
Thanks for the description of standardization processes. It takes a long time for sure. In TC82, we have no lifetime standard up to now, but we have type approval standards for silicon and for thin film solar cells. And they are going to be merged in the next step, because the mainly difference is the characterization of the different technologies in terms of performance. So the structure will be that the stress tests are pretty the same, because they are applied to the same climate or other stress, and only the measurements are different. So I could imagine that OPV would be treated in the same way if it is intended to deliver power by exposing it to the ambience.
And I fully agree, and we have a liaison with TC82. We're talking about this, who should be doing what, and I'm sure you're familiar with that. Anyhow, so eventually, as we get to this stage where we're nearing a product, I absolutely have the same opinion. Then this is something that should be done in TC82. But I think we're in a place that is far away from that. And right now we simply need some guidelines. And I think we need to make them referenceable. And that's the goal here.
Would be helpful if you would define stability a little bit more precise, whether it's characterization or whether it's long-time durability.
It's very simple. We're defining degradation conditions, and the reported number is T80 under these conditions. So the time it takes to get to 80% of the initial efficiency, and that's stability under these particular conditions. And that is a number that, in our opinion, is comparable. It has nothing to do with type approval. It has nothing to do with product testing. It's not meant for that.
Okay, if not, let's think. Oh, one more.
If there's no question, I would just like to answer to your direct criticism of my talk. I totally agree with you that you cannot derive from this light soaking it under sulfur plasma lamp a lifetime of 20 years. I just said it's the message that it can convert light into electricity for a light dose which corresponds to such times. So if this was not clear, I'm totally agreeing with you. It's not if this was not clear. It's not my intention to give this picture.
It was not meant as a direct criticism to you or anybody. It's just we have to be careful with these terms, and I've experienced that firsthand. And lifetime is just oftentimes mistakenly used. So that's all I was trying to say. And it wasn't just you. I saw it in different places. So.
Okay, I saw one more question, Dana.
Coming from an institution that goes across technologies quite readily, I think, you know, to kind of put a different spin on your kind of interpretation of lifetime. One of the issues that we've had with using lifetime in terms of stability testing is that most of the other technologies actually think of lifetime as something very, very different in minority carrier lifetime.
Yes.
And so I absolutely agree in the sense that it actually helps kind of distinguish between these two spaces, just in terms of communication with other technologies as well. Otherwise, yeah, I mean, a lifetime being predicted is something very different from something that's been measured, which I think is more your point as well. So.
Yeah.
One more question. Okay. Maybe quick.
I'll try to be quick, but probably a bit more general question. Thanks, Jens, for the talk. Well, the whole process of setting up the standards, of course, as you said, going to take a few years probably. So I was wondering if you could sort of give some recommendations to the scientific community then what we really should do in meantime. And perhaps again I keep raising this question about what is the role of the scientific community here in the entire process, because when you say consensus, obviously all are involved in this, but how we could generally, I know that there's the official procedure through the national institutions, but how we generally could, everyone around, contribute in the process somehow. Yeah. If you could comment on that. Thanks.
Yeah. So first of all, I think this community has done actually extremely well, because you do see that the ISO's paper and these ISO standards, they are being quoted. You do see them used in the literature. So I think that's excellent. It's always important to also give feedback. Is there something missing? Is there something else that should be added? There's always this discussion that I'm trying to avoid. What are good conditions versus bad conditions? I think there's some better and there's some worse ones, but certainly you want to stress something enough so that you actually that you can actually measure some degradation. Otherwise, it's not worth much in terms of development cycles. But you also don't want to overstress devices. So what I think is very important, for example, as a message are things that I've seen today on this 85-85 testing, that it's possible to go to 85-85. And yet, in some like we're designing there, I think we still shouldn't recommend only one temperature. Probably in the end, we'll recommend several temperatures that you can use, because it is meant as something that gives you valuable feedback. And you know, if it fails within 4 hours, that makes it easy to measure, and that makes it nice because you can get fast turnover cycles. But that's obviously not the goal. So any feedback over what are good tests and what are bad tests, or good directions, bad directions, is always useful. There's still plenty of room to steer here. What is also important is maybe as a feedback is what other directions, where else are maybe some standards or some documented procedures, where are they missing? How can we help from the standardization side to actually aid progress here?
Okay, thank you very much. Thank you, Jens, for starting such an interesting discussion. Let's thank Jens again for the interesting presentation.